Hello everyone, thanks for joining me on this adventure from classical to quantum. Today's a very important lecture because I'm going to be initiating a new way of thinking about the transition from so-called real to so-called complex analysis with regard to Fourier series, harmonic analysis on circles and spheres, and then leading to quantum mechanics. These topics are intimately interwoven, and if we understand Fourier series or harmonic analysis in a better way, it has direct applications to a wide variety of topics which are central in quantum mechanics, including the harmonic oscillator, the hydrogen atom, and the quantum version of angular momentum. All of these end up being potentially completely redoable. We're going to be able to see them in a completely new light once we adopt a more rational, a more finite, a more algebraic approach to harmonic analysis on circles and spheres. And a key ingredient to that program we're going to initiate today in moving to introduce complex numbers into the story. Now, it's one of the enduring mysteries of quantum mechanics that somehow in the 1920s and 30s, people realized that this new theory of quantum mechanics somehow intrinsically required complex numbers. And many people have speculated, why is that? So we're going to provide a partial answer in that direction today, that it's somehow connected, perhaps, at least in part, with the natural role that complex number analysis plays in understanding the harmonic analysis of the circle and spheres. So we're talking about S1, which is the ordinary circle, x squared plus y squared equals 1 in a two-dimensional affine plane. But there's also S2, the unit sphere, x squared plus y squared plus z squared equals 1 in a three-dimensional space. And of course, we can continue S3, S4, etc. spheres, unit spheres in higher dimensional spaces. And in fact, S3 plays a very important role in this discussion, as we'll see. So Fourier series initially is regarding the expansion of functions on the circle. We're interested in describing rather general functions in terms of combinations of relatively simple functions. So we want to identify functions which are sort of very simple to deal with and use them as building blocks to cook up and analyze more complicated functions. Okay, so that whole story then generalizes to things called spherical harmonics on spheres. And so there's a classical treatment of this story, but we are going to circumvent that. Okay, I'm going to give you an alternate way of thinking about this entire framework, which avoids all those transcendental functions, avoids irrationalities altogether. Remarkably, even the number pi is not going to get involved. We're going to be able to do all of this without any mention of pi, except mentioning that we're not actually using this. Okay, and so we're ultimately going to be even being able to work in this very general situation of looking at the n-dimensional sphere, Sn, which maybe we could introduce some more systematic notation, say x1 squared plus x2 squared up to plus xn plus 1 squared equals 1. This is in an n plus 1 dimensional affine space, and this is the unit sphere. So today I want to talk about the general framework here and then move towards explaining why it is that complex numbers appear already here in this very simple case in S1. So it becomes crucial actually to understand complex number arithmetic, to understand the Fourier series story on the circle, and then that naturally ends up playing a big role also for the higher dimensional spheres. In fact, once we have this idea of having these spheres sort of stacked up one after the other, starting with a circle, it naturally occurs to us to maybe also include the zero-dimensional sphere, okay, which we call S0, which is just the equation x squared equals 1 occurring in a one-dimensional situation. So here's a one-dimensional affine space, x, there's 0. Here's the point 1, here's the point minus 1. These are the two solutions to this equation. So in this case, this zero-dimensional sphere just consists of 2 points. Just 2 points. So that turns out to be also part of the story, and it's an interesting sort of starting point. So now we can maybe think about relabeling things a little bit, actually, because we want things to be consistent with what we're doing here. So it actually makes sense for us to relabel things in the following way. So instead of using X and Y and Z or X1, X2, let's use the alphas, because we're working in a polynumber framework, okay? And we can actually connect with box arithmetic. So if you don't know about box arithmetic yet, make sure to go over to Insights into Mathematics and start looking at the box arithmetic videos, which are in the Math Foundation series. This is a very important development, okay? And what we're doing here naturally connects with that. But it won't be necessary for you to understand that. But what we're going to do is we're going to introduce these polynumbers called alpha 0, alpha 1, alpha 2, and frame everything in terms of them. So S0 is just the equation alpha 0 squared equals 1. S1 is alpha 0 squared plus alpha 1 squared equals 1. S2 is alpha 0 squared plus alpha 1 squared plus alpha 2 squared equals 1. There's S3, and so on, obviously. So now Sn will be alpha 0 squared all the way up to alpha n squared equals 1, sitting inside n plus 1 dimensional affine space, which we can now think about as being given by points of this form, x0, x1, up to xn. Okay, does that make sense? It's quite pleasant. So there's actually a containment hierarchy of spheres going on here. We may regard the various spheres as contained in each other, in the sense that the equations, when you restrict them to the lower variables, give you the lower dimensional spheres. So we can think about S0 as being inside S1, being inside S2, being inside S3, etc. So we have this sort of family of spheres that sort of go up in dimension. And in some sense, we can perhaps imagine an object at the end of this story. Now, usually I'm nervous about, going to infinity. And I insist that, the objects that we are talking about should really be finitely specifiable. So how do I deal with something like this? Well, what we can say is that this is the equation expressed this way here. So this is the equation alpha 0 squared plus alpha 1 squared plus alpha 2 squared, and so on, equals 1. But what does that mean? Does that mean we're adding an infinite number of things? No, it doesn't. It means that we're actually looking at a condition in this infinite dimensional affine space. So the corresponding affine space will consist of sequences like this, x0, x1, x2, etc. Potentially, going on very far, but with the requirement that only a finite number of non-zero terms are in this sequence. So it's all zeros, essentially, except just a finite number of non-zero ones. So that means if we are looking to see whether such a point satisfies this equation, only a finite number of these alpha terms are going to be relevant, right? So it always reduces to a finite computation. We have finite points, but the sizes of those, the lengths of those points is not prescribed. They can be arbitrarily long. And so we still have a condition of that satisfying this sphere condition. So this is a way for us to bring into reasonably tight mathematical being some kind of limiting phenomena. It's very interesting, without ever pretending that we can do an infinite number of things. So what kind of picture do we have here? Well, it's challenging to think about this, but let's just have a look at the three-dimensional situation. Okay, so maybe x0, x1, x2 here. Okay, they have the axes. And just along the x0 line, we see these 2 points, like 1 and -1. That's S0. Then if we restrict ourselves to the x0, x1 horizontal plane, we get this circle. That's the usual unit circle S1. And then in the three-dimensional space, we see S2. So here we have S0 contained in S1, contained in S2. But then we can imagine this thing just being part of, or a slice of, some higher dimensional thing. So if we go up one dimension, say, to four-dimensional affine space, we imagine taking this three-dimensional piece and sort of slotting it in as this sort of horizontal wedge. Now that's not an accurate, pictorial description, but okay, just imagine this three-dimensional thing is sitting inside this sort of slab here. Okay, so the S2 that I've pictured here is sort of sitting as sort of an equatorial object there, and now we have this new direction, say x3, and then we can define S3 in terms of the horizontal equator and this new x3, and it's given by the usual formula. So you end up with this picture, and you can keep on going, of sort of introducing higher and higher dimensions, but always these spheres are contained in each other. So there's a possibility of sort of trying to understand this harmonic analysis on these spheres almost perhaps in the same fashion, or in a uniform way that kind of incorporates all of them at once, possibly. Now, just for future reference, I want to point out that there's a possible analogous sort of hierarchy where the circles or spheres are replaced by hyperbolas or hyperboloids. And that just involves a little bit of a change of sign here and there. So we start with h0, which has equation alpha 0 squared equals 1. Okay, that's familiar. And now h1 we could define as alpha 0 squared minus alpha 1 squared equals 1 in 2 dimensions. So that's a hyperbola. And then contained in h2, which is given by this equation, alpha 0 squared minus alpha 1 squared minus alpha 2 squared equals 1 in 3-dimensional space. Contained in h3, given by this equation in 4-dimensional space. And we could keep going. So we can imagine a kind of a corresponding family of hyperboloids, being stacked up in higher and higher dimensions. And there's also alternatives, because in this situation here, it might sometimes be interesting to replace the 1 with a minus 1, okay? But in any case, I just want you to keep in mind the possibility that as we proceed understanding harmonic analysis on circles and spheres, maybe some of that intuition or analysis will sort of be translatable to the hyperbolic situation, okay? In fact, if we do things right, and we do things in a nice way, then that will amplify the possibility of having such a nice transition. And then we'll be able to see a lovely parallel between these two stories. And while we're talking about further directions and things that you might like to think about, you could also say, well, you can see a pattern here. Maybe we could do something one step further. Like maybe we could, instead of having one positive coefficient and then a whole bunch of negative ones, maybe we could have 2 positive coefficients. Like the alpha 0 squared and the alpha 1 squared always have positive signs, and then all subsequent ones have negative signs. There's going to be a whole hierarchy of those too, aren't there? There are also kind of hyperbolas, but they're of somewhat different nature. And in fact, you could, in principle, consider yet another family where you have k of these which are positive, and then all subsequent ones are negative. But in each case, you're getting towers of these things. You're not just getting one, you're getting a whole tower. And the question about harmonic analysis on these things is hugely interesting, okay? And I would say largely unexplored, especially from the point of view that I'm going to be explaining to you, okay, the algebraic, completely rational point of view. So there's just so much work to be done here. And this is really quite directly relevant to physicists, because hyperbolas and hyperboloids are very important for physics, okay? And the non-compact nature of them as compared to the compact nature of the sphere, it's an interesting distinction. And when we start to do harmonic analysis on them, questions of normalization naturally sort of connect with issues of normalizations in physics, of trying to deal with infinities that come up. So anyway, there's a lot to think about here if you're a student of mathematics, physics. All right, great, so we have all these potential directions. But all of these investigations come back to starting with the circle. We want to understand the circle in the right way. That becomes so critical. And I have to be honest with you, right? The way you see Fourier series and harmonic analysis discussed in modern texts, and especially in pure mathematics, is almost uniformly wrong. Okay, it's just wrong. Because it supposes that we have to introduce transcendental parameters like an angle and corresponding transcendental functions like cosines and sines, and then the higher dimensional spherical harmonics. We're going to be able to do this whole story without any of that. Okay, so this is a different picture. It's the same subject, but I'm giving you a different picture, an algebraic picture. Okay, so just a bit of notation. So we say thinking about alpha 0 squared plus alpha 1 squared equals 1, or sometimes maybe more conveniently just alphas and betas. So alpha squared plus beta squared equals 1. There's our unit circle. And here is our favorite differential operator, the Laplacian. d0 squared plus d1 squared. So d0 squared is the second derivative with respect to this one. d1 squared is the second derivative with respect to this one. Or in terms of alphas and betas, more colloquially in text, it would be d squared d alpha squared plus d squared d beta squared. Okay, so that's an operator. And then we have various function spaces. So the general space that we're interested in, so the universe of discussion here for the two-dimensional situation, is the world of bi-Pauli numbers. Script P. So there's a bi-Pauli number. It's a polynomial, if you like, in alphas and betas. And we'll generally write them with increasing degree. And the top term here is this one here. It's of degree 4. So this is of degree 4. So we define P of n. It's a polynomial in here, a bi-Pauli number, whose degree is less than or equal to n. So this would be in P4. This is also in P5 and P6, etc. And then we can consider also homogeneous polynomials. That's a polynomial where they're all of the same degree. So, if it was of degree 4, there'd be terms with alpha beta cubed, but there might also be terms with alpha to the 4th, or alpha squared, beta squared, or beta to the 4th, okay? So those are homogeneous ones, and if they're homogeneous of degree n, we put the n as a subscript, so that's Pn. And then there are corresponding harmonic versions of this, where we restrict ourselves to those bi-Pauli numbers that have the very important property that they are killed by the Laplacian. That is, you apply the Laplacian to them, you get 0. Okay, so the ones in here, the general bi-Pauli numbers of degree less than or equal to n, we'll call h of n. So these are the p's in here, which the Laplacian kills. And correspondingly, h sub n are the p's in here, the homogeneous polynomials of degree exactly n, which are killed by the Laplacian. These are the harmonic bi-Pauli numbers. And you might say, well, why are we interested in these particularly? So that's a good question. Okay, we haven't explained that yet. That will become apparent as we carry on. But it turns out that it's exactly these bi-Pauli numbers that have the property that when you restrict them to the circle, you get a nice basis of functions or polynomials on the circle. Okay? So if you look at all the bi-Pauli numbers on the ambient two-dimensional space and restrict them to the circle, there's a lot of duplication. Because, for example, the Pauli number alpha squared plus beta squared and the Pauli number 1 agree when you restrict them to the circle. So they have the same values. They look the same as functions restricted to the circle, even though as functions on the plane, they are very different. So to get rid of that sort of redundancy, it turns out that the harmonic condition is exactly what we need. Okay, so that's some advanced explanation of why these are so important. But we'll see that that will unfold as we carry on. All right, now we come to this long-standing, mysterious question about why are complex numbers so intrinsically important in quantum mechanics? Now, I don't have a complete answer to this, but we're going to see a partial answer. So in general, very quickly, a quantum system is somehow described by a wave function, psi, which is complex valued. So it's a function that takes on complex values. And the evolution of this wave function with respect to time is given by Schrödinger's equation. However, when you observe the wave function, when you observe the system and you measure something or other, then typically you expect a collapse of the wave function. So the sort of smooth progression that the Schrödinger equation suggests is interrupted, and something more perverse and sort of discrete and jarring happens. And that's really a central conundrum of quantum mechanics, is to somehow bring these two things together, explain why do we have these two completely different kinds of things that can potentially happen to a wave function. Now it turns out that when you have one of these collapses of the wave function, that the outcome that you get is somehow a particular state, but it's not determined. There's a certain probabilistic aspect to what you can obtain when you make a certain measurement on a quantum system. And it turns out that the probability distribution of the possible outcomes is determined by this value psi squared, the complex number quadrants, essentially, okay, of the quadrants number, is determining the probabilities of various final states after collapse. So the complex numbers are encoded in the wave function, which evolves in a complex number kind of way. But when we measure something, then somehow only the real or the rational part of the wave function, if we're working in a rational world, becomes relevant. So that's sort of an embodiment of, we don't see the complex numbers directly, but they're there sort of hidden under the surface, it appears to us. Why? So let's bring complex numbers into the story. Let's extend our coefficients of our polynomials or polynumbers to allow complex number coefficients. So we're going to consider CP. This will just denote the space of polynumbers or bipolynumbers in our two-dimensional situation with complex coefficients. For example, this thing here, 2 plus I minus 3I times alpha plus 4 plus 7I beta squared, etc. Okay, so in this rather larger domain, we can now make a simple but important change of basis. And it's this one here, where we introduce U to be alpha plus I beta, and V to be alpha minus I beta, which is just the complex conjugate of U. This is a linear change of variables. And inverting it, we get alpha equals, if we take the sum of these two, well, the betas cancel, and then we get 2 alpha. So alpha is equal to U plus V over 2. And if we take the difference, well, then the alphas cancel, and we get beta equals U minus V over 2I because of that extra factor I. So this is an invertible linear change of variables. And that means that if we say look at the homogeneous bipolynumbers, say of degree n, which have a traditional basis alpha to the n minus 1 beta, etc., up to beta to the n, all the terms are of degree exactly n, then an alternate basis is obtained with u's and v's. So u to the n minus 1v, u to the v n minus 1, up to v to the n. And the reason I hope is clear, because if we have a polynomial in these things, a linear combination of these things, then just by replacing alpha and beta by these expressions here, we get a corresponding bipoly number in u and v of exactly the same degree. And conversely, if we have a linear combination of these things and we replace the u's and v's with these expressions, then we're going to get a bipoly number in alpha and beta of exactly the same degree. And if we want to, sometimes it's convenient to look at the corresponding factorial basis. So that's just as valid in the u's and v's as it is in the alphas and betas. So u to the n underscore, it just means u to the n over n factorial, while this one here, u to the n minus 1v underscore, means we actually dividing by n minus 1 factorial times 1 factorial, just as before. All right, so this is just a simple change of basis, but it has a lot of interesting algebraic consequences. A lot of things become actually somewhat dramatically simpler from this new complex point of view. So one important relation is that if we take the product of u and v, which is basically u times its complex conjugate, so we're getting the quadrants of this thing, which is alpha squared plus beta squared. And in particular, if we think of this as a function on the plane, then if we restrict it to the unit circle, then it's going to have value 1 identically. Okay, so now we have a complex basis for the space of bipoly numbers in the plane, but the complex space of bipoly numbers given by 1 and u and v, that's sort of the degree 0 ones, the degree 1 terms, u squared, uv, and v squared, the degree 2 ones, u cubed, u squared v, u v squared, v cubed, the degree 3 ones, etc. Okay, so the span of these things, we could call that CP2. These are the bipoly numbers which are of homogeneous degree exactly 2 with complex coefficients. All right, so now we come to a very important calculation that probably every student of mathematics, and maybe of physics also, ought to make at least once in their career. That's to calculate the Laplacian acting on this monomial u to the m, v to the n. Okay, So u to the m, that's that thing there, alpha plus I, beta to the m, there is v to the n. And the Laplacian is the second derivative with respect to alpha plus the second derivative with respect to beta. Okay, so let's do it sort of one step at a time. Let's take the just the first derivative of all of this. Okay, the first derivative of alpha, so there'll be a d alpha times the first derivative here, which is okay. If we take the derivative, we get an m times this thing here to the m minus 1. So this drops by a degree, and we still have to multiply that. And then the product rule is also, we also have this term here times the derivative of this, which is an n times this thing here to the n minus 1. Okay, so that's the d alpha squared acting on this. The d beta squared is d beta of this. So applying the derivative with respect to beta, the m comes down, and then we get an m minus 1, but the coefficient in front of beta has to come out front because of the chain rule. So we get an I there, all right, times this term here as well. And then the product rule, also this thing here, times the derivative of this with respect to beta. So the n comes down in front, but so does the minus I. And then this thing here to the n minus 1. Okay, now we go back up to this thing and take the derivative of this with respect to alpha again. Okay, here the m minus 1 comes down, and we get this thing to the m minus 2. Well, this is u, so let's just write u to the m minus 2, and here is v to the n. But we also have to do it the other way around, so we have to take the derivative of this thing, okay, times this. So m times n, then u to the m minus 1, and this one drops to v to the n minus 1. Okay, now we go over here. Again, the product rule, the derivative of this, there's an m, so an m times n, times u to the m minus 1, it's dropped by 1, this stays where it is, v to the n minus 1. Plus, we leave this thing where it is, that's u to the m, and we take the derivative of this with respect to alpha. So we get an n minus 1, so there's an n times an n minus 1, and then this drops to give us v to the n minus 2. And now, same thing, we're going to apply the d sub b to this thing here. Okay, so taking the derivative with respect to beta, it's the product rule. So the derivative of this one first, there's an m minus 1 coming down, but also an I. That I coming down will multiply with that one to give us a minus sign. So there's a minus m times m minus 1. Then u to the m minus 2, and this stays as it is, v to the n. In the other order, if we take this thing here just by itself, u to the m minus 1, and differentiate this with respect to beta, well, there's a minus I that comes down. The minus I times that I is minus I squared, which is plus 1. Okay, so we don't get a minus sign here, there's a plus. And we get a v to the n minus 1. The n, of course, comes down, so we get m times n times this thing here. And now we look at this second term here. We take the derivative with respect to beta, so there's an m coming down, there's an n already here, but there's an I that comes down, multiplying by the minus I, gives it just a plus sign. So we get u to the m minus 1, v to the n minus 1. And then the final term, we leave this one where it is and take the derivative of this one with respect to beta. So the n minus 1 comes down, and we get another minus I. Okay, but now we have a minus I times minus I. That's the same as plus I squared. Plus I squared is the same as minus 1. So there's a minus sign appearing there. We get an n minus 1 coming down, u to the m stays where it is, v to the n minus 2. Okay, and now we look and see that this thing here and this thing here are the same, but with opposite signs because of that minus sign, so they cancel. And this one here at the end and this one here are the same, but one has a minus sign, so they cancel. We only have these intermediate terms, and they're all the same. They're all m times n times u to the m minus 1, v to the n minus 1. So the conclusion is that Laplacian acting on u to the m, v to the n equals 4 times m times n times u to the m minus 1, v to the n minus 1. And strictly speaking, there are some caveats because we're not really allowed to get negative exponents here. So if n was equal to 0, then this would not really work. So we have to say for m and n bigger than or equal to 1, just to avoid that. However, there's a way of rewriting this to shift to the factorial notation. So if we replace the u to the m, v to the n by u to the m v to the n underscore, that really means there's an m factorial, n factorial there. That's the same as taking this expression and dividing both sides by m factorial, n factorial. Okay? Then what we get on the right-hand side is for u to the m minus 1, v to the n minus 1 underscore, because the m and the n will cancel with what's down here to give us m minus 1 factorial times n minus 1 factorial. And the pleasant aspect of this is that this turns out to be true for all integers m and n. So there's no proviso that we have to restrict ourselves to certain values. This is just a uniform. So when it comes to the Laplacian, and the action of the Laplacian, working with this factorial basis is pleasant. But both of these are really, really nice formulas because they're simple. The Laplacian acting on one of these terms is just a single other term, not a sum of terms. So we are able immediately to see what actually the harmonic polynumbers are in this complex basis. The harmonic ones are just the span of these sort of pure powers of u and v, the ones that don't involve both u and v, but just a single one, either just u's or just v's or just one. So in terms of our diagram, they're just the things on top of the picture. They're the outer layer, the boundary layer. That's what the harmonic bipolynumbers look like. And the reason is, well, first of all, we know these ones are all harmonic because the previous formula told us that. If one of the, say, if the u term is 0, and we think about the underscore notation, then we apply the Laplacian, then there's a factor of 0 that appears, so it becomes 0. And why is it that there's no harmonic polynomial possible by taking some linear combination of these guys, which are sort of underneath? Well, the action of the Laplacian is as indicated here with these green arrows. The Laplacian on this is, well, it's not just this one, but it's this one times some multiple, 4 times the product of the powers here. But in particular, it's non-zero, right? So the Laplacian acting on this will be a non-zero multiple of this one. So suppose that you have a linear combination of these interior ones, so underneath the red boundary. Say 3 times this one minus 2 times this one, and you apply the Laplacian. Well, the Laplacian of this is some multiple of that. The Laplacian of this is some multiple of that. So we're going to get 3 times some multiple of this minus 2 times some multiple of that. And that can't be 0 because these are all independent. All of these guys are independent. There's no linear relationship between any of these guys. So there's no way that can be 0. So there's only one way of getting harmonic bipolynumbers in this basis. That's just to take some linear combination of the ones which are outside. And this simple, relatively simple understanding immediately sort of lays out most of the important facts about harmonic analysis on a circle, as we'll see in our next video.